Not one of the sealed rock containers Apollo brought back from the moon was still holding vacuum when it reached Earth. Not one. The best sealing technology of the 1960s applied to the most valuable cargo in the history of spaceflight, defeated by dirt. That single fact should have told everyone what kind of problem a moon base really is. And 54 years later, an agency running a lunar program measured in tens of billions of dollars finally acted on it. In February 2026, NASA canceled a rocket stage it had been developing for more than a decade. It canceled the launch tower built to carry that stage, contracted in 2019 for $383 million, promised for 2023, and by 2026 costing more than $1 billion, with delivery slipped to the end of the year. It paused Gateway, the station it had spent years designing to orbit the moon. And it announced that Artemis 3, the mission meant to put boots back on lunar soil, would no longer go to the surface at all. Then, 4 weeks later, the same agency stood in Washington and announced something far larger. $20 billion, 7 years, a permanent base near the lunar South Pole, with habitats, pressurized rovers, and nuclear power. Administrator Jared Isaacman described 2 landing missions a year, building toward continuous human presence. Cancel the heavy hardware, commit to something an order of magnitude harder. Read side by side, those 2 announcements look like an institution contradicting itself in a single quarter. They are not. They are the same decision, made by people who had finally finished calculating what the moon does to machinery, and discovered that the hard part of a lunar base was never the rocket. The obstacle to a permanent lunar base is not launching to the moon. We solved that in 1969 with slide rules. The obstacle is that the moon attacks every category of infrastructure at once: power, thermal, seals, optics, bearings, coatings, human tissue. And it attacks them on a schedule that does not care about fiscal years. Every fix for one failure adds mass. Every kilogram of mass adds launches. Every launch adds cost. Every cost overrun adds schedule. And schedule, on a program measured in decades, eventually crosses an election, a new administrator, a new budget, and the engineering resets. That loop is the actual subject of this video. Not rockets, not astronauts planting flags. The compounding failure chain that turns a construction project into a permanent negotiation with physics and appropriations at the same time. We are going to walk through it in order. The dust that destroys seals, the exhaust that turns soil into shrapnel, the 14-day night that eats power budgets, the heat that has nowhere to go, the radiation that limits how long a human ledger stays open, and the supply chain that does not yet exist. Then we will follow the money through the contracts, the cancellations, and the other base being built on the other side of the geopolitical map. By the end, you will be able to read any moon base announcement and see the constraint underneath it. Start with a word everyone uses and almost nobody defines. Permanent is a load-bearing word. On Earth, it means a building stands until someone demolishes it. On the moon, it means something closer to a hospital intensive care unit, a machine that keeps a fragile thing alive and which fails the moment the machine stops. Break it into requirements and the abstraction disappears. A permanent base needs continuous electrical power because the moment power drops, thermal control stops and the hardware freezes. It needs continuous thermal control because vacuum removes the option of simply venting warm air. It needs pressure integrity across every hatch, joint, and glove, maintained against a vacuum that never lets up. It needs consumables: oxygen, water, food, carbon dioxide scrubbing media, filters. It needs spare parts because every mechanism on the surface has a shortened life. And it needs a resupply cadence reliable enough that the interval between deliveries is shorter than the time it takes for a critical system to fail unattended. That last requirement is the one that quietly sets the entire budget. Isaacman's framework describes roughly 2 landing missions per year. Compare that to McMurdo Station in Antarctica, the closest analog humanity has to a permanent outpost in a hostile environment. McMurdo receives cargo by ship and aircraft, is supported by a supply chain measured in thousands of tons annually, sits inside a breathable atmosphere, and still requires continuous maintenance to remain habitable. A lunar base gets a fraction of that mass, at several orders of magnitude more cost per kilogram, with no possibility of an unplanned resupply flight. This is why serious lunar architecture documents read less like exploration plans and more like logistics spreadsheets. The question is never, Can we build a habitat? Pressure vessels are mature engineering. The question is how many kilograms per year the base consumes to stay alive, and whether the transport system can deliver that number reliably, forever. And here is where the physical environment enters the accounting. On Earth, the consumption rate of a facility is mostly a function of what the people inside use. On the Moon, it is dominated by what the environment destroys. Seals, bearings, coatings, radiators, optics, fabric, the surface degrades all of them faster than any terrestrial equivalent. The base does not merely consume supplies, it consumes itself. To understand why, you have to start with the material that covers the entire surface, several meters deep, and behaves unlike any dust on Earth. In December 1972, geologist Harrison Schmitt became the only trained scientist to walk on the Moon. He spent about 22 hours outside across 3 excursions in the Taurus-Littrow Valley. When his suit came back to Earth and was examined, engineers found that lunar dust had abraded a hole clean through the pressure garment above his boot. His sunshade was so scratched he could not see through it in certain directions. Dust stiffened his joints, jammed his zippers, and coated every surface it touched. Then came the finding that should have reframed the entire problem. Apollo returned rock samples in containers sealed with indium knife-edge seals, a design intended to hold hard vacuum all the way back to Houston. Not one of those containers from any Apollo mission held vacuum on return. The most likely explanation is simple and brutal. Dust grains settled on the sealing edges, and the seals could not close against them. Understand what that means. The most carefully handled, highest value cargo in the history of spaceflight, sealed by the best sealing technology available, defeated by dirt. Now imagine a habitat with airlocks cycling twice a day for 30 years. The reason lunar dust behaves this way is that it was never weathered. On Earth, wind and water round every grain over time. Sand is smooth because it has been tumbled for millennia. Lunar regolith is the product of micrometeorite impacts, breaking rock into angular fragments in vacuum, with nothing to soften the edges. The grains are sharp, glassy, and extremely fine. They also carry electrostatic charge from solar ultraviolet exposure, which makes them cling to surfaces rather than fall away. You cannot brush it off. You cannot blow it off, because there is no atmosphere to blow. The Apollo crews reported it clogging vacuum equipment, insulating batteries, and pushing them toward overheating, making Velcro useless, and defeating mechanisms across the board. Schmitt himself developed what he called lunar hay fever after inhaling it in the cabin, and every one of the 12 people who walked on the surface reported some reaction. Translate this into an operating cost, and the picture sharpens. Every rotating joint on the surface is a consumable. Every optical surface degrades. Every fabric layer thins. Every seal is a scheduled replacement. A base is not one machine, but thousands of interfaces, and this environment is grinding all of them simultaneously. That is the maintenance burden nobody budgets for on Earth, because on Earth, it does not exist. And dust is not only a slow problem. Twice per landing cycle, it becomes a fast one, moving at velocities that turn soil into shrapnel. In November 1969, Apollo 12 executed the most precise landing of the program, touching down roughly 180 meters from Surveyor 3, a robotic probe that had been sitting on the surface since 1967. The crew walked over and cut pieces off it to bring home. When those pieces were examined, engineers found something they had not fully anticipated. The Surveyor was damaged, and only on the side facing the Apollo landing site. The surface was pitted with tiny holes where grains had punched through the paint, with cracks radiating outward from each impact point. The descent engine had turned the ground into a directed blast of particles. Estimates of ejective velocity vary widely across studies. Early figures were around 40 meters per second. Later analyses bounded the minimum above 70 to 100 meters per second, and some modeling puts the fastest particles far higher. What is not in dispute is the direction of the effect. A lander arriving on unprepared regolith sandblasts everything within line of sight. Now apply that to a base designed around 2 landing missions per year, forever, at a single site. Every arrival and every departure fires abrasive material across the installation. Solar arrays lose transmission. Radiators lose the optical properties they depend on to reject heat. Camera lenses fog permanently. Seals collect grit. The very cadence that makes a base sustainable is the cadence that degrades it. The engineering answer is obvious and unhelpful. Build landing pads. Prepare a surface so the Plume hits something solid instead of loose soil. But building a pad on the moon means either sintering regolith with concentrated energy, or manufacturing paving elements from local material, or landing prefabricated pad hardware from Earth. The first two require substantial electrical power and autonomous construction robotics. The third requires exactly the heavy cargo landings that need a pad in the first place. That is the paradox in its cleanest form. You need infrastructure to protect infrastructure, and the only way to deliver the first piece is to do the damaging thing. There are proposals to mitigate it: landing inside natural craters so the rim absorbs the ejecta, spacing landing zones kilometers from the habitat, building berms. Every one of them costs distance, and distance on the moon costs pressurized rovers, power, and time. There is no free version. There is only choosing which cost you pay. And whichever you choose, you will pay it in electricity. Which brings us to the constraint that has broken more lunar architectures than any other. Most of the moon runs on a cycle of roughly 29.5 Earth days, about 14 3/4 days of continuous sunlight, then about the same length of continuous night. During that night, with no atmosphere to hold heat, surface temperatures fall to roughly -173 degrees Celsius. Not for an hour, for 354 hours without interruption. Solar panels produce nothing for that entire period. So the system must store energy, and this is where the physics turns hostile. Thermal engineering analyses of lunar night survival converge on a punishing rule of thumb. Keeping just 1 watt of continuous power available through the lunar shadow requires on the order of 5 kilograms of battery. A modest 100-watt survival load, enough to keep electronics warm and alive, implies hundreds of kilograms of battery mass, doing nothing but preventing death. Scale that to a habitat drawing tens of kilowatts, and the battery mass alone exceeds the payload capacity of any lander currently flying. The failure mode is not gradual. If a system runs out of stored energy at hour 100 of a 354-hour night, components cool below their qualified limits, materials contract at different rates, solder joints crack, and batteries themselves are permanently damaged by deep cold. Hardware that goes dark on the moon usually does not come back. This is not theoretical. Commercial landers that lost power at lunar sunset have simply never responded again. The standard escape route is geography. Near the lunar south pole, there are ridges and crater rims, sometimes called peaks of eternal light, where the sun stays above the horizon for a much larger fraction of the cycle because the moon's axis is barely tilted. Park your solar arrays there, and the night problem shrinks dramatically. But those locations are small. They are not perfectly continuous. They still experience blackout periods, and, critically, they are exactly the same terrain everyone else wants. A resource that is both physically scarce and strategically valuable stops being an engineering variable and becomes a diplomatic one. Hold that thought. There is one power source that does not care whether the sun is up. It works in shadow. It works inside permanently dark craters. It works for a decade without resupply. And in 2025, the United States government formally decided it was no longer optional. In August 2025, NASA's then acting administrator, Sean Duffy, issued a directive that changed the shape of the lunar program. It ordered the agency to design, build, and deploy a fission reactor on the lunar surface, producing at least 100 kilowatts of electrical power, ready for launch by the first quarter of fiscal year 2030. Reactor designers were told they could assume a heavy-class lander capable of delivering 15 metric tons. The number matters more than the deadline. NASA's earlier fission surface power work, contracted in 2022, had been calibrated around 40 kilowatts. The directive more than doubled that. Doubling the power target in a nuclear system is not a scaling exercise. It changes the core design, the shielding mass, the radiator area, the power conversion approach. The directive specified a closed Brayton cycle for conversion, which means turbines spinning in a sealed loop on a surface covered in abrasive dust, with no maintenance crew for the first several years. Why double it? The stated logic is written into the directive itself. It notes that if another nation deploys a reactor first, that nation could establish keep-out zones around its installation, which could significantly inhibit United States operations. And the 2029 to 2030 target aligns with China's publicly stated goal of landing astronauts on the moon by 2030. Follow the money on that sentence, and the engineering becomes strategy. A reactor is not just a power supply, it is a physical claim on the small number of locations where a base can work: near the water ice, near the near-continuous sunlight, near stable terrain. Under the Outer Space Treaty, no nation may claim sovereignty over lunar territory, but nothing in the treaty prevents a country from placing hardware somewhere and then requesting, on safety grounds, that others keep their distance. Article 9's principle of due regard becomes, in practice, a negotiation about buffer distances. For the industrial base, this is a first-of-a-kind program, with all the cost behavior that implies. There is no production line for compact space reactors. There is no flight heritage for a 100-kilowatt fission system on a planetary surface. There is a nuclear launch approval process that runs through the executive branch. There are fuel supply questions, transport licensing questions, and radiator geometry that has to survive both the launch environment and the dust environment. Every one of those is a schedule risk, and schedule risk on a program with a hard external deadline converts directly into cost. Which is worth stating plainly because it is the pattern that repeats throughout this story. Nothing here is impossible. Reactors work, landers work, habitats work. What compounds is that each solution imports a new failure surface, and the new failure surfaces interact. The reactor solves the 14-day night. It also generates roughly 3 units of waste heat for every unit of electricity it delivers. Heat that, on a body with no air and no water, has exactly one place to go. Every thermal engineer who has worked a lunar program says a version of the same thing. The hard part is not keeping warm. It is getting rid of heat. On Earth, 3 mechanisms move heat: conduction, convection, and radiation. Convection does the heavy lifting in almost every machine you own. Air or water carries energy away from a hot surface. In vacuum, convection does not exist. Conduction only moves heat into whatever the object is touching. And lunar regolith is one of the best insulators in the solar system, with thermal conductivity comparable to aerogel. That leaves radiation. A lunar base can only shed heat by emitting infrared into space, through radiator panels sized by the Stefan-Boltzmann relationship, where rejected power scales with area and with the 4th power of temperature. That single equation drives an enormous amount of hidden mass. A 100-kilowatt reactor, rejecting a few hundred kilowatts of waste heat, needs radiator area measured in hundreds of square meters, deployed, structurally supported, and plumbed with working fluid. Habitats need their own. Every electronics box needs a thermal path to somewhere. On the ISS, the thermal control system is among the largest and most maintenance-intensive subsystems on the station, and the ISS sits in an environment far friendlier than the lunar surface. Now add the local complications. Radiators depend on optical properties: high emissivity to radiate, low absorptivity so sunlight does not heat them back up. Those properties live in a coating a few microns thick. Coat that surface in electrostatically cleaning dust, and performance falls permanently because there is no rain and no practical way to clean hundreds of square meters by hand. A radiator that has degraded 20% does not announce itself. It simply narrows every margin downstream. Then add terrain. At the South Pole, the sun sits near the horizon, which is helpful for solar power and unhelpful for radiators because low-angle light strikes vertical panels directly and the surrounding ground stays warm enough to radiate back. Designers end up pointing radiators at cold sky or into permanently shadowed terrain, which constrains where hardware can sit and how it must be oriented. Geometry that would be trivial on Earth becomes a siting constraint that ripples into the entire base layout. Here is why this belongs in a story about systemic breakdown rather than a textbook. Thermal control is invisible in press releases. Nobody announces a radiator, but it consumes mass, area, power for pumps, and maintenance attention. And it is coupled to the dust problem, the plume problem, and the power problem simultaneously. Change any one of them, and thermal has to be redesigned. That coupling is precisely why lunar architectures get re-baselined so often, and why a program that changes its plan looks indecisive from outside, while being entirely rational from inside. Machines can tolerate a degraded margin. The other system on the base cannot. In 2019, China's Chang'e 4 lander carried an instrument called the Lunar Lander Neutrons and Dosimetry Experiment to the far side of the moon. It produced the first direct measurement of the radiation dose on the lunar surface, published in Science Advances in 2020. An average dose equivalent of about 1,369 microsieverts per day. That number deserves a moment. It is roughly 2.6 times the daily dose received by crew aboard the International Space Station, and it is dominated by galactic cosmic rays, high-energy particles arriving continuously from outside the solar system. The ISS sits inside Earth's magnetic field, which deflects a large fraction of charged particles. The Moon has no global magnetic field and no atmosphere. On the surface, roughly half the sky is blocked by the ground beneath you. The other half is open. Cosmic rays are the chronic exposure. The acute risk is different and worse. During a large solar particle event, dose rates can spike by orders of magnitude over hours. On Earth, and even in low Earth orbit, this is a manageable inconvenience. On the lunar surface, without a shielded volume to reach quickly, a major event during a surface excursion is a serious medical scenario. The engineering response is mass. Shielding works by putting material between the human and the particle flux. And for cosmic rays, hydrogen-rich material works best. Water, polyethylene, or simply a great deal of regolith piled over the habitat. Nobody plans to launch that shielding from Earth because the mass is prohibitive. The plan, in essentially every serious architecture, is to bury the habitat. Use robotic equipment to move a few meters of local soil over the pressure vessel, which means excavation machinery, operating in abrasive regolith, powered by the reactor, maintained by a crew whose time on the surface is limited by the very radiation the shielding is meant to reduce. That is the ledger, and it closes in an uncomfortable loop. Radiation limits how long a person can stay. Shorter stays mean more frequent crew rotation. More rotation means more launches. More launches mean more landings, more Plume events, more dust across the installation, and more cost per unit of useful work. Meanwhile, the construction that would reduce the radiation exposure requires human oversight in the early phase, when the shielding does not yet exist. None of this makes a base impossible. Astronaut career dose limits exist precisely so agencies can plan around them, and mission durations can be set to stay inside them. But it does mean that the human presence, the entire point of the exercise, is the most tightly rationed resource on the surface. Every hour of crew time is expensive, radiation limited, and dependent on hardware arriving on schedule. Which raises the question the whole architecture rests on. Can anything actually get there reliably? A permanent base is a delivery problem wearing an engineering costume. And the delivery system for the current American lunar plan is the most ambitious logistics chain ever attempted. SpaceX's Starship human landing system does not fly to the moon on a single launch. It launches to low Earth orbit, then is refilled with cryogenic propellant transferred from a series of tanker flights to an orbital depot. Public estimates of how many tanker launches are required vary considerably. Commonly cited figures run from roughly 10 to 16, with some analyses going higher. SpaceX has conducted initial ship-to-ship propellant transfer work, with a full-duration orbital demonstration expected in 2026. Until that demonstration flies, the number of tankers required is an estimate, not a measurement. Consider what that architecture asks for. Each tanker must launch, rendezvous, dock, and transfer super-cold liquid oxygen and methane in microgravity, a technique that has never been performed at this scale. The propellant in the depot boils off continuously, which means the launches cannot be spread out casually. They have to occur within a window, in sequence, with high reliability. A single failure in the chain does not delay one flight. It can force the whole sequence to restart. Blue Origin's Blue Moon takes a different path, with its own dependencies. And the February 2026 restructuring pointed Artemis 3 toward orbital rendezvous and docking demonstrations with one or both commercial landers, precisely because those capabilities had not yet been proven. That is what a course correction looks like when the demonstration schedule and the mission schedule finally diverge too far to reconcile. Now layer the base on top. 2 landing missions per year is not a lot of mass. Against that, you have consumables, replacement seals, replacement bearings, filters, radiator panels, spare pumps, science equipment, and crew. Every subsystem discussed so far, dust-degraded mechanisms, sandblasted coatings, batteries damaged by cold, radiators losing emissivity, generates demand for that same limited cargo. The base competes with itself for mass. And there is no surge capacity on Earth. A facility with a broken pump orders another one. On the moon, the replacement arrives when the next launch window, the next lander, and the next fully fueled depot align. This is why lunar logistics planners talk about spares philosophy the way hospitals talk about blood supply. You do not stock what you expect to use. You stock what you cannot survive without, which makes the reliability of the delivery vehicles the single most consequential number in the entire program. Fortunately, we already have data. Unfortunately, the data is sobering. Between 2024 and 2025, NASA's Commercial Lunar Payload Services program did something unusual for a space agency. It bought lunar deliveries as a service from private companies, accepted that some would fail, and published the results. Those results are the closest thing we have to an actuarial table for lunar landing.
Astrobotic's Peregrine launched in January 2024 and suffered a propulsion anomaly traced to a valve. It never reached the moon. It re-entered and burned up over the Pacific. Intuitive Machines' IM-1 Odysseus made it to the surface in February 2024, the first American soft landing since Apollo, but a landing leg failed and the vehicle tipped over. It operated, but at reduced capability with antennas pointed wrong. Intuitive Machines' IM-2 Athena landed in March 2025 and also ended up on its side, in a location where its solar panels could not see enough sun. It lasted roughly 12 hours before the batteries died. Between them, Firefly's Blue Ghost Mission 1 landed upright on March 2, 2025, and, according to the company, completed 100% of its mission objectives, operating through the lunar day and returning data until it powered down at sunset. So, of the first 4 attempts, 1 fully succeeded, 2 landed but were compromised in ways that gutted their mission value, and 1 never arrived. Take that record at face value and ask what it implies for a base that needs 2 cargo deliveries a year to stay alive. It implies redundancy, and redundancy is expensive. It implies that critical spares must be split across multiple flights, so a single failure does not strand the base without a component it cannot live without. It implies stockpiles on the surface, which means storage volume, which means more mass. And it implies that the schedule everyone quotes publicly is a best case that assumes a reliability level the industry has not yet demonstrated. There is a fair counterargument, and it deserves to be stated. These were first attempts by young companies at fixed prices deliberately set low, and every one of them produced engineering data that the next vehicle inherits. IM-2's landing problem was attributed in part to altimeter interference and to the punishing lighting conditions near the South Pole, where long shadows and low sun angles confuse optical navigation. Those are solvable. Reliability curves in aerospace do improve steeply with flight count. But notice where the difficulty concentrated. Not in getting to the moon, in the last few hundred meters, on unfamiliar terrain, in bad light, at the exact location the base is supposed to be built. The South Pole is where the ice is. It is also the hardest place on the moon to land. Which brings us to the resource that justifies the entire address. Everything about the South Pole, the bad lighting, the long shadows, the difficult landings, the crowded terrain, is tolerated for one reason. There is water there. Orbital radar and neutron measurements from NASA's Lunar Reconnaissance Orbiter and India's Chandrayaan-1 support estimates on the order of 600 billion kilograms of ice in the polar regions, concentrated in permanently shadowed regions where crater floors have not seen sunlight in billions of years, and temperatures stay below about 110 Kelvin. More recent analysis suggests ice deposits extend well beyond the immediate pole to at least 77 degrees south latitude, with roughly 5 liters of ice per square meter in the top meter of regolith in some areas. Water is the single most valuable substance on the moon, and not mainly for drinking. Split it and you get oxygen to breathe and hydrogen and oxygen to burn. A base that produces its own propellant stops importing the heaviest thing it consumes. This is the promise of in-situ resource utilization, and it is genuinely transformative if it works, because it inverts the logistics equation that makes everything else expensive. Now, read the fine print. 5 liters per square meter in the top meter is not an ore body in any terrestrial sense. It is a dispersed trace resource, requiring the movement of enormous volumes of frozen, abrasive soil. The material sits at temperatures cold enough to make steel behave unfamiliarly, in permanent darkness, where solar power is by definition unavailable, and every machine must carry its own light and its own heat. Extracting water thermally means heating regolith, and heating is the most energy-intensive thing you can do. Research on beneficiation, concentrating the icy fraction before processing, exists precisely because the straightforward thermal approach demands so much power. So the chain closes, ice reduces launch mass, extracting ice requires power. Power in permanent shadow requires the reactor. The reactor requires a heavy lander. The heavy lander requires the propellant that ISRU was supposed to provide. Every element of the architecture is waiting on another element, And the sequencing of that dependency graph is the real design problem, far more than any individual technology.
This is what distinguishes a lunar base from a lunar mission. A mission is a straight line. Launch, land, do the thing, come home. A base is a network with feedback loops, where the value of each node depends on nodes that do not exist yet. Engineers call this the bootstrapping problem. Economists would recognize it as an infrastructure investment with a very long payback period and no intermediate revenue, which is exactly the kind of project that human institutions are worst at financing. The physics has been consistent for 60 years. The money has not. And to understand why the plan keeps changing, you have to look at how the plan gets paid for. Return to that launch tower. Mobile Launcher 2 was contracted in 2019 at $383 million, with delivery expected in 2023. By 2026, its cost had grown to more than $1 billion, and delivery had slipped to the end of that year. Then, in February 2026, NASA canceled the rocket configuration the tower was built to launch. The tower became surplus before it was finished. That is not an isolated line item. A NASA Office of Inspector General interim memo issued in June 2026 examined 4 Artemis systems with a combined contract value of roughly $5.9 billion that the agency had announced plans to cancel or repurpose, including the Exploration Upper Stage and Mobile Launcher 2. The memo's subject, Managing Programs and Projects After Mission Termination, tells you the institutional problem in its title. Zoom out further. A GAO assessment of NASA's major projects published in July 2026 put the agency's portfolio at least $70 billion in estimated life cycle costs. The same body of work documented something less discussed. NASA reduced its civil servant workforce by about 4,000 people in 2025, roughly 22%, and 25 of 36 major projects reported effects from that reduced staffing. Put those 3 facts together, and a mechanism appears. Hardware for a lunar program takes 10 to 15 years to design, qualify, and fly. Funding arrives in annual appropriations. Leadership changes with administrations. Requirements change with leadership. So the engineering is asked to hold a stable configuration across a period during which nothing else stays stable. When the configuration finally changes, work already paid for becomes surplus, and the accounting records it as a cancellation rather than as the accumulated cost of instability. Nobody in this chain is behaving irrationally. A contractor bidding a first-of-a-kind system under a fixed schedule is pricing genuine uncertainty. An administrator who inherits a program running years late and billions over is making a defensible call by rebaselining it. A Congress funding annually is doing what the Constitution set up. The failure is not located in any one actor. It is a property of the system, a long-cycle engineering problem financed on a short-cycle political clock. And that is the second meaning of systemic infrastructure breakdown. The first is physical: dust, plume, cold, heat, radiation. The second is institutional, a decision loop that runs faster than the hardware it decides about. The two amplify each other because every physical surprise triggers a redesign, and every redesign consumes schedule, and schedule is exactly what the institutional clock refuses to give. There is one obvious way to break that loop. Run the program on a clock that does not reset every 4 years. Someone is trying exactly that. China's lunar program is organized around a plan called the International Lunar Research Station, and its structure is worth studying, regardless of what you think about the politics. The published architecture divides the effort into phases: reconnaissance from roughly 2021 to 2025, construction from 2025 to 2035, and utilization from 2035 onward. Chang'e 7 targets the South Pole region for environment and resource survey. Chang'e 8, planned for 2028, is explicitly a technology mission, testing in situ resource utilization and construction methods, and evaluating base sites. A crewed landing is targeted by 2030, using the Long March 10 heavy-lift rocket and a next-generation crewed spacecraft. A basic version of the station is targeted for completion by 2035, with an expanded version envisioned by 2045. Notice the sequencing. Survey the site. Test resource extraction and construction on the site. Then land people. Then build. It is the order a civil engineering firm would use, and it is deliberately unglamorous. No crewed landing before the robotic groundwork is done. Notice also the timeline. 24 years from first survey to a basic station. That is longer than most American program plans, and it is precisely the duration that a system of annual appropriations and 4-year leadership cycles struggles to sustain. Whether the schedule holds is a separate question. Space programs slip everywhere, and China's has slipped before. But the planning horizon itself is the variable worth watching.
Now connect it back to the Reactor Directive. That directive explicitly raised the concern that another nation deploying surface power first could establish keep-out zones that inhibit United States operations. This is where engineering, law, and geography collide. The Outer Space Treaty of 1967 prohibits national appropriation of celestial bodies. It does not prohibit placing hardware, and Article 9 obliges parties to act with due regard for the corresponding interests of others. Language that, applied to a nuclear installation, reasonably implies a safety perimeter. The scarcity makes it sharp. The terrain that works, near continuous sunlight, proximity to permanently shadowed ice, stable ground, benign landing approaches, is a small number of ridges and crater rims near one pole. Two programs optimizing independently will converge on overlapping sites because physics gives them the same shortlist. What happens then is not written anywhere. There is no lunar traffic authority, no adjudicating body for surface claims, no agreed buffer distance around a reactor or a landing zone. There is a treaty written before anyone could build there, a set of political accords signed by some parties and not others, and a short list of good real estate. That is a governance gap, and it will be filled by whoever arrives first and by whatever precedent they set. Which raises a question almost nobody asks about permanent bases. Assume it works. Assume the reactor lands, the habitat is buried under regolith, the pads are built, the extraction plant makes water, and the first crew rotates through. What is the failure mode of a lunar base that has already been built? It is not an explosion. The realistic failure mode is dormancy, a base that is functional, expensive, and quietly abandoned. We have precedent. Skylab was operated for less than a year of cumulative crew time and re-entered in 1979 with no successor ready. Mir was deliberately deorbited in 2001 while still working because operating it competed with a newer program. The International Space Station, arguably the most successful long-duration facility ever built, is planned to end in a controlled, destructive re-entry rather than be handed to anyone, because nobody wants to pay for its maintenance. In each case, the hardware did not fail. The funding case did.
A lunar base introduces a new wrinkle. It cannot be deorbited. It will sit exactly where it was left, essentially forever, in a vacuum that preserves everything. If maintenance stops, the sequence is predictable. Batteries die in the first night. Seals lose integrity as materials cold soak past their limits. Radiator coatings continue degrading, and the site becomes an industrial ruin, holding the most valuable terrain on the moon. That last part is the strategic consequence. An abandoned base still occupies a peak of eternal light. An inert reactor still implies a keep-out radius. Under a due regard framework, hardware that no longer works may still generate an obligation to stay clear of it, which means the first builder does not only get first use. The first builder can foreclose the best sites even after walking away. Nobody is proposing this outcome, and no plan targets it. But it is the natural endpoint of the loop we have traced all video. Physical systems that degrade continuously, financed by institutions that decide in 4-year increments. Maintenance debt accumulates silently, and the moment it exceeds political appetite, the base does not close. It simply stops being visited. If this is the kind of question you find worth sitting with, where engineering, money, and geography stop being separate subjects, this channel exists for exactly that. Subscribe if you want more of it, and if there's an infrastructure story you think deserves this treatment, put it in the comments. Some of the best subjects covered here started as a single line from someone watching. Now let's close the loop and name the actual nightmare, because it is not any of the individual problems we have covered. Every problem in this video has a solution. That is the part that makes it a nightmare rather than a tragedy. Dust can be managed with electrodynamic dust shields, hardened coatings, redesigned seals, suit port airlocks that keep the suits outside the habitat entirely. Plume ejecta can be mitigated with prepared pads, crater rims used as berms, landing zones sited kilometers away. The 14-day night can be defeated with fission power. Waste heat can be rejected with enough radiator area. Radiation can be reduced by burying the habitat under a few meters of local soil. Logistics can be improved with orbital refueling and higher flight rates. Ice can be extracted with sufficient energy. Every single one is an engineering problem with a known direction of attack. The nightmare is that they are coupled. Solve dust with more airlock complexity, and you add mass and maintenance. Solve night with a reactor, and you add waste heat, shielding, and radiator area. Solve radiation with buried habitats, and you add excavation robots that consume power and are themselves destroyed by dust. Solve landing damage with prepared pads, and you need heavy construction equipment that must be landed on unprepared ground. Each solution is locally correct and globally expensive, and the total mass grows faster than the transport system improves. Then the second loop closes on top of the first. Growing mass grows cost. Growing cost extends schedule. Extended schedule crosses political cycles. Political cycles change requirements. Changed requirements rebaseline the design. And rebaselining resets the engineering that was in progress, which is how a launch tower contracted at $383 million ends up costing over $1 billion and being canceled before it is used, and how roughly $5.9 billion of hardware becomes surplus in a single announcement. That is the systemic infrastructure breakdown, not a bridge collapsing. A design loop and a funding loop running at incompatible frequencies, with a physical environment that never stops applying load. Which puts the $20 billion over 7 years in its proper light. It is not an outlandish number for what it buys. Habitats, pressurized rovers, nuclear surface power, and the logistics to sustain them near the lunar South Pole. Measured against the physics, it may well be optimistic. Measured against the institutional record, the harder question is not whether the engineering can be done. It is whether any political system can hold a single technical configuration steady for the 15 years the hardware requires. 60 years after Apollo, that remains the unsolved problem. The moon is not waiting for better engineers. It is waiting for a decision that outlasts the people who made it.